Hello everyone, my name is Amir. I'm a software engineer. I currently don't have any affiliation, but I will have one in the next couple of weeks, so you can ask me next time you see me what my affiliation is. I'm going to present this competition on Recruit restaurant visitor forecasting. In case you're wondering what is the word recruit doing in the title of the competition, the reason is that the sponsor of this competition is a Japanese holding company named Recruit Holding Company, and that's why there's the word recruit in the title. The challenge is, given the visitor data and in reservation data to a set of restaurants in Japan, predict the number of visitors to each restaurant in future days. And the prize money for the competition is $25,000. That was divided between the top 3 ranking teams, and more than 2,100 teams participated in the competition. That was, I think, running for about 4 or 5 months. So this holding company that I mentioned, they operate 2 SaaS products in Japan. One of them is called Hot Pepper Gourmet, which is a restaurant reservation and information, kind of similar to Yelp in Canada or the US that we have. You can search for restaurants based on location, based on cuisine, and you can also make reservations there. And part of the data comes from that source. The same company also operates another SaaS product for restaurant management and reservation management for restaurants. It is called AIR. We will refer to it as AIR in our data, and HPG, the first one. This has data about visitors, number of visitors to restaurants, as well as reservations. So in this case, people would call a restaurant and make a reservation. In the first case, they would go online and make a reservation. Okay. This is the data set, pretty much. All the features fit on one slide. As you can tell, it's a small data set in terms of dimensions, but also in terms of number of training data points. It is a small data set. What I like about this data set is that it has a small dimension. So for a presentation like this, you get to spend more time on each individual feature, try to look at each feature to see what it has. And also, people tend to get creative when you don't have a lot of features. People tend to mix and match existing features to come up with something, another feature that helps them win the competition. So that also makes it interesting. And finally, this data set encodes a part of human behavior that is going to restaurants and partying and eating and drinking. And I find that part of data science interesting. So for me, this particular data set was interesting. All right, now looking at the features, we have reservation data that is coming from Hot Pepper Gourmet. Nothing very complicated there. Store ID, time of reservation, timestamp when the reservation was made. So the difference is that one of them is when the person, for example, called the restaurant and made the reservation, and the other one is when the reservation was made, right? So there's a difference here. And the number of seats that were reserved. Then we have the restaurant information that is coming from both data sources, from both HPG and AIR. Store ID genre, they call it genre or type of restaurant. You'll see what genres there are later. Then we have area name, which is some word, latitude and longitude. So this is for the restaurant information. Then we have visitors that's coming from only from one data source, that is coming from AIR, from the restaurant management software. Date, store ID, and number of visitors. Right? And then we have calendar info that says what day in the calendar, in Japanese calendar, was a public holiday. So this holiday flag is a binary flag. That is 1 if that day was a public holiday, and it's 0 if it's not a public holiday. There are a total of 829 restaurants in the AIR dataset, and Hot Pepper Gourmet has a larger dataset. You can imagine this is because not all of the restaurants in this data set, in HPG data set, are actually using a restaurant management software. They may not be using any software at all, or they might be using a different software. All right, okay. This is the training and test data. Remember that we are dealing with time series data in this case. So we have all of these features not all of them, but reservation and visitor features that are the main features we are talking about. They happen every day for each restaurant, right? So we have data points for each day during this training and test data. And of course, this is what we have to figure out. So the training data goes from all the way from January 2016, all the way to the end of the third week of April. And the test data, which is this red part, is the last week of April and all of May. Now, there's something tricky here about this part of this time frame, this part. And it's because this part of this test time frame spans over this 1 week in Japan that is called the Golden Week. And it's 1 week of festivities and celebrations. There's Emperor's Birthday, and I don't know, there's Children's Day and Constitutional Memorial Day, things like that. And so there's more holidays happening this week, and people tend to go crazy. There's a lot of partying and going to restaurants happening. And so this turns out to be the key to winning this competition. So keep this in mind, we'll talk about it later. This is the format of the expected submission file. Pretty simple. There's the ID of the restaurant underscore the day for prediction, and then your prediction for the number of visitors to that restaurant for that day.
Does that ID have any comprehensible information in it?
No, it doesn't. It's just a random generated ID.
Okay.
Yeah. Something that I probably should mention here is that the latitude and longitude of restaurants are somewhat anonymized. They wanted to anonymize the restaurants. So for each individual restaurant, they have, for all of the restaurants in the same neighborhood, they've given the same latitude and longitude. So you can't exactly map information to each restaurant, okay? So latitude and longitude are somehow representative of the restaurant's coordinates, but they are not exact. And they may be the same for a set of restaurants in one neighborhood.
Given that you also know the genre of the restaurant and other sort of identifying information, although it's down to the nearest neighborhood, surely you'd be able to reverse engineer that potentially.
Yeah.
Did you see anyone sort of attempting that? Or?
I didn't see any of that, but I can imagine people have done that. I can very well imagine.
So you have the amount of visitors to the restaurant, but was there also seating capacity or hours of operation?
No, you don't have that.
Okay.
You don't have that, yes. That would be, yes.
Yeah.
I'm still confused about the training data, if you can go back.
This one?
After that one. Yeah, so I get that there's, 4,000 restaurants, but the data is presumably reservations. So how many reservations are there over the year and a quarter?
How many reservations?
Is the data reservations?
So this is reservations. This is only reservations.
Oh, I see. So it's 4,000 reservations, 800 restaurants.
Yes. So
Gotcha.
yeah, no. So this data set only has reservations, right? This is the Yelp, right? So sort of these number of restaurants exist in this data set, right? But this is the main data set. The main data set is AIR, because it's only this data set that has the actual number of visitors, right? So there are restaurants in here that also exist in here. Right? So for every restaurant, let me put it this way. So for every restaurant in AIR, you have the number of visitors, right? And you also have some reservation information here. And then you also have some extra reservation information for those restaurants coming from HPG data set. Does that make sense?
The AIR database is a subset of HPG?
That's correct.
Or can contain also other restaurants that were not having reservation?
Yes, so the restaurants in air, the set of restaurants in air is a subset of set of restaurants in HPG.
Okay, thanks.
Well, the thought I had was how to make use of those restaurants in HPG that aren't in air, but I guess that you'll be getting to that a little bit.
Yes, so the test set only targets restaurants in air. Yeah, maybe that's what I should mention. This is the main data set. Think of it as an auxiliary data set. Yeah, so the target comes from air. Probably that addresses the confusion. This is the evaluation metric. It is root mean square logarithmic error. Take a couple seconds to look at the formula before I tell you more about it. So it's somehow different from the more familiar root mean square error that we are used to. There are two interesting things about this metric. One of them is that it penalizes under predictions more than over predictions, which kind of makes sense. There's an example of that. So here, if the true numbers, if the ground truth is 1,000 and the prediction is 600 under prediction, the penalty is more than the case when we predict 1,400, we over predict. So RMSE is giving the same penalty, whereas RMSLE is giving higher penalty to under prediction, which kind of makes sense in this context because you'd think that restaurants prefer to be over prepared rather than under prepared, right? So that's one interesting property that this metric has. The second interesting property is that when the numbers are bigger, when the ground truth and the prediction are both bigger numbers, the penalty gets smaller. So again, I've put an example there for you. So if the actual number is 1,000 and prediction is 1,400, the penalty is much larger than when the actual number is 10,000 and prediction is 10,400, right? Again, it makes sense because bigger restaurants have more tolerance for mispredictions, right? Whereas smaller restaurants have less tolerance. So the amount of penalty is adjusted based on the number of visitors restaurants can handle. I thought this was an interesting thing there to mention. All right, so let's look at the data. This is the first diagram coming from the data. It's showing you the total number of visitors across all the restaurants for the duration of the training data. There are a few things to notice here. The first thing is this step here. And unfortunately, there is no explanation for this step by the providers of the data set. People have only speculated, like, maybe there was a campaign here happening by this company, and then a lot of people bought into the product. Maybe I don't know. They merged two different data sets and merged it. So, anyways, there's this mysterious step happening here, which we don't have any explanation for. Some people chose to ignore all of the data before this time. Some people chose to use the data. So the first thing. The second thing to notice is that dramatic plummet here that you see, this drop here, which is we can explain it by a lot of restaurants not being operational on the first day of January. And you can also see the same thing happening here. So that is also easily explained. And the second thing to notice is this periodic behavior of the number of visitors that we will talk about in the next slide. This is the distribution of the number of visitors across all the data points. It's interesting that you see the mean of the number of visitors to restaurants is 20 and the median is 17. So it's surprising to me that there are a lot of restaurants that get so few visitors on a day. That's very interesting.
My comment on probably having so few visitors is there's quite a few little tiny restaurants in Japan that might only have 8 seats in them. So
Yeah, yeah. I've never been to Japan. I can imagine from the pictures that I've seen and things that I've heard, I think there are a lot of like smaller shops, smaller restaurants in every neighborhood, every corner. I think that's what is explaining this data. I think somebody else, yeah.
Would you comment on the period of the oscillations in the?
Yes, yes. That's a very important thing that I will tell you about in the next slide.
Yeah, what's the period and?
Yeah, it's on the next slide.
Oh.
Yeah, yeah. Sorry? Yes, it's the days. Yeah, if you're, okay, I'll move on to the next slide. So, yeah, so this final diagram you've been waiting for some time. Yeah, so as you predicted, it is there's a cycle there. People start from depressing Mondays and then get crazy and excited as they progress towards Saturday, and they party like crazy on Saturdays and Sundays, and then you go back to depression on Mondays. So this is easily explainable by that. That's an interesting thing, although not unexpected, but it's interesting observation. There's not a lot of variation across months. Naturally, you can think that people go to restaurants more often in summer and spring and less often in fall and winter. And also December is party time, so you can see that here. Again, there's nothing surprising there. This is the number of reservations, so the number of seats reserved across this time. Again, you see some weirdness in data, like a flat line here, and then it's, again, not explained. There's nobody has clear explanation for it. And my point of showing this here is that using reservation would sometimes not help you and might even actually cause a challenge. A lot of people have, as far as I can tell, a lot of people chose to actually use the data set, this data. Yes, Alex?
Did anybody try to normalize these two periods?
Normalize the time series?
It seems like the pattern is the same, it's just the volume is different, so basically making it like, I don't know, 3 times bigger, 4 times bigger.
Yeah, no, I didn't know actually. This confused a lot of people. I didn't see anyone being able to make sense of this. If you're talking about removing
just basically taking anything like before, I guess, August 2016 and just adjust it like, in terms of volume.
Yeah,
does that make sense?
I didn't see anything on that.
Okay,
yeah.
thanks.
Were you expecting something to show if you normalized?
No, just you said that some people just ignored that period of time, just dropping that data, which is, I think, stupid because I think in both graphs that you showed, the patterns are kind of the same. Especially on the first one, it was like, it seems like the pattern is the same, it's just the volume is different.
Yeah.
Basically, if you take a medium or like mean of the period after July 2016 and calculate that median, then take the median for previous period and then just, multiply that by the difference, right? So I don't know, like it's just something I thought maybe.
Yeah, I mean, so notice that this is reservations, and some of these make sense. Like, I don't know, the same trend around December. Probably people start making more reservations around December, towards the end of the year, maybe for, again, festivities. Some of it makes sense, but some of it, like this, I really don't know what's happening here. Like, there's no data whatsoever.
So those are straight zeros?
Yeah.
Maybe it was shut down.
Yeah, maybe I don't know.
Is it because like a holiday week or something like that?
Not that long. Yeah, this is like a 2.5 months. Yeah. Yeah, unfortunately, they don't explain it. They just, yeah. This is probably this couple of diagrams are my favorite diagrams coming from this data set. So on the left, we have the distribution of time between the time reservation was made and the time of reservation. So if I call a restaurant today and make a reservation for tomorrow, this difference between today and tomorrow is a data point whose distribution is plotted on the left, right? Okay, so you see that a lot of people go to restaurants around 6, 7, 8 in the evening. And then on the right is the distribution of this data point. So the distribution of the data point that I just mentioned, right? So this is interesting. This is, I think this is a fun diagram. You can make different observations about this. So notice that there's like clusters of people. Some people are very timely. They like make a reservation 4 days in advance because this is like 4 days, right? 100 hours is almost 4 days. And then there's like less orderly people and then people who are, last minute, people who make late reservations. So that's one thing that's interesting. And the second thing is that people actually are not very comfortable making a phone call in the middle of the day because probably they are at work. So these are like midday boundaries, right? So this is like a day and a half, right? And you see that there's like this kind of behavior that you see people are not making phone calls. And this data is not coming from HPG. This distribution is coming from AIR, that reservations only happen by phone calls, okay? So this is a fun diagram. This map shows where the restaurants come from. They come from major cities in Japan. Yeah, just so you know. And these are restaurants. On the top, you see all of the genres. There's, in case you're wondering what is the top one, is Akaya. I looked it up. It is Japanese pub. That is the casual go-to place for, casual drinking place for after work. That's probably why it is so popular. And I have to say, in the cuisines, I'm curious about creative cuisine. I don't know if you have any idea what creative cuisine is. I just find it curious. All right, so this is for genres, and these are the top 15 most popular areas. I guess these two diagrams together mean that area and genre are important features that we should be engineering and incorporating into our model. And this is the breakdown of the total number of restaurants for different genres. Notice that the y-axis is logarithmic, so just pay attention to that. You see that the trend is steady for some genres, like Italian, French, and Japanese food is pretty steady. For some other genres, like party, for some reason, seems to be going in and out of fashion for some reason. And teppanyaki is very, very unpopular on the first day of January. Yeah, so again, another indication that genre should be used as a feature. So it's another takeaway from this diagram. This is the diagram shows the impact of holiday flag on the number of visitors. You see average number of visitors for different days a week. And you see for Saturday and Sunday, the holiday, if it's like a public celebration or something, it doesn't really change much. But for weekdays, it has a large impact, right? So like, especially for Monday, Tuesday, people just go crazy. They just go to restaurants a lot. So you see that. Again, takeaway is that the importance of holiday flag is high, so we should also take it as a feature. And this is the last diagram coming from data. Yeah.
Can you go back a couple of slides? One more. Yeah, here. Here we don't see the change in the middle of the year or an earlier.
Yeah,
slides
the drop.
The drop. You don't see the drop here.
That's a good point. I don't know. I don't know. Just notice that maybe this is responsible for it.
But that's like just one of a couple of them. Okay.
Well, okay, good, great. Actually, I think we found it. Nobody found this.
Wow.
Awesome.
I should have participated. Oh, thanks.
Awesome. Good question. See, that's what I like about these meetups.
On the following slide, I was wondering what the standard deviation is on those numbers of visitors.
I don't know. A breakdown by restaurants?
On the following slide, one after.
This one?
Yeah.
I don't have the number. I can probably just dig it up for you like in a sec, but I don't have it.
The question was, asked what the standard deviations were for the next slide. That was what the question was.
Yes, I should repeat questions. Yeah.
Turn it on.
In the next slide, what are the colors?
In this slide?
Yeah, this slide.
Yes, so green means holiday. Holiday flag is set. Red means holiday flag is not. I apologize for not mentioning that clearly. Actually, I'm still excited about this. I'm so excited that we found it. For some reason, international cuisine and party was not in the data set prior to that date. Interesting. Okay. All right, so this is the last diagram for this data. This plots the total number of visitors on y-axis against the number of seats reserved on x-axis. Now, prior to seeing this diagram, I would think that there would be a lot of data points above this line, which is the case, because I would think that a lot of people make reservations and then they go to restaurant. A lot of people don't make any reservations, they just drop in. And so the total number of visitors to a restaurant would be more than the number of reservations, seats reserved throughout the restaurant, which is the case in a lot of cases, but actually a lot of cases it is not the case. So in a lot of cases, restaurants get more seats reserved than the actual reservations. And it's crazy. So and there are some extreme cases, like in this case, 90 seats reserved, and the actual number of visitors to restaurant is like 5 or less than 5 or 10. And I feel bad for those restaurants. I'm wondering if this is something that is more common in Japan, or if anyone has an insight on this, if it's like a common thing that's commonplace in Canada everywhere, I don't know. That's interesting. So many reservations that people don't show for, or they just cancel last minute. Yes.
Maybe there are competitors that try to screw that.
Yeah, I don't know, maybe, yeah. Oh, your competitor makes a call and makes a reservation, they don't show. I see now. It never occurred to me, yeah. Yeah, so this is interesting. Okay, now let's take a step away from the competition and look at the general context of time series prediction, or prediction on time series. Let's talk about that. So there are 3 categories of techniques for prediction on time series that I will very briefly talk about, very briefly. The first one is the category of the so-called additive models, like ARIMA and friends are in that category. Holt-Winters is another. These models were invented in 40s and 50s, mainly by economists, for predicting trends in financial markets. And I'll tell you a little more about these categories. The second category is the more recent category of random forest and boosting that people use for this competition. I'll tell you more about it also this one. And deep learning, not surprisingly. Time series prediction is a more recent application of deep learning. And I have a couple of slides on that. I'll probably have time to go over those slides. All right. Before I talk about the models, I should also mention something that we should know when we are dealing with time series, and that is creating a k-fold cross-validation data set. Now, remember that we are talking about sequence in the data. So we want to make sure that our cross-validation data set is also respecting the sequential semantics of the data, right? And so because of that, the way to create k-fold cross-validation data set is by defining a window that shifts from the beginning of the data, and the amount of shift kind of increases gradually, as you can see here. And if you ever want to do that, scikit-learn has a function for you to create a k-fold cross-validation data set. All right, now having said that, we can start looking at time series prediction using linear models. So ARIMA is a very popular technique. It is relatively easy to understand. You can actually look it up on Wikipedia. It's more or less easy. So there are 2 main ideas in this thing. The first idea is that next values in your time series regress over your previous values. So in other words, you can formulate a linear regression that calculates your next values based on your previous values, right? So that's idea number one. The idea number two is that the error of this linear regression is a linear combination of previous values error, okay? Kind of more or less the idea. And I will skip over the third one. There is a library from Facebook that's called Prophet. It's very friendly. It exists. It has Python and R bindings. It's fun to play with if you want to take a look at it. All right, so naturally, a lot of people started with ARIMA for time series prediction. These are three examples, predicting the number of visitors for three different genres. And you see that for some genres, like dining bar, it actually does a pretty good job in predicting. For izakaya, it's kind of so-so, and for teppanyaki, it does a terrible job. In general, people said that it doesn't really work very well for this data set. Let's go ahead.
So this will just regress based on the values, but it won't use any of the features that you have about the restaurants?
Yeah.
Like
it
doesn't care if it's a holiday, nothing.
No.
Just it looks at the signal.
Exactly, just one feature that is the number of visitors in the past. Yes, pretty rudimentary, I'd say. Yeah, so this was a dead end. Everybody pretty much very easily, very quickly concluded that this is not the way to go. All right, so that was from linear models. Now, moving on to deep learning. There's a lot here to cover. It's like I said, it is relatively new. The earliest paper on this topic that is notable goes back to 2014. People have been using RNNs mostly, but convolutional neural networks have also been recently suggested for this. And the main purpose of that has been for speech synthesis. Interestingly, there was another competition running during the same period of time that people who came second they published a paper on their solution, and they actually use a convolutional neural network that is inspired by Google's WaveNet. They published a paper on it. The code is on GitHub. It's very interesting. I'm going to skip over the neural network part. Unfortunately, I have to do that. All right, so moving to features. Let's go back to the competition and talk about features. So these are sort of obvious features that everybody figured out. Store ID, year, month, day of the week. Statistics on number of visitors, holiday flag, number of reservations and reserved seats, time difference between the time of reservation and window statistics over all of these numbers, right? Very easy features. And then there are more interesting features that some people reported to be useful. Popularity of the neighborhood, how many restaurants are in those neighborhoods, competition in the neighborhood, meaning how many similar restaurants in the same genre exist in the same neighborhood. They took it as a surrogate for competition in that neighborhood. And the area name. Turns out that area names in Japan have a hierarchy, or at least in the way they are presented in the data set. And so people said that using that prefix and infix in the name can actually give you a boost. And weather data, some people brought in external data sources that was allowed for this competition. And then what I call surprising features that I would never have imagined work. People said the sum of latitude and longitude for each restaurant actually gives you better results. You tell me why. And then somebody else, actually the second solution used both of these features. The second feature is the difference between latitude and longitude of each restaurant and the max in the entire data set. I have no idea what this means, but people reported that it works. Anyone has an explanation, I would appreciate that.
I would guess that adding the longitude and latitude, it just checks whether you are on the diagonal that Japan seems to follow.
Okay.
So it must be that the more northeastern you are in Japan, I don't know.
Wouldn't longitude account for that by itself? Like, why do you have to
Yeah.
Yeah, might be because
So I can only guess, adding longitude and latitude, it seems weird, but I don't know if you had some area that was like boxy and it happened to be like that upper right part or wherever the max was the more popular area, then maybe there was some wacky logic to it there, but I don't know, it does seem weird.
Yeah, I mean, given that rest coordinates are kind of approximated to the same for all the restaurants in the same neighborhood, yeah, I know.
Did anyone use other data like weather? Weather would be a good one, surely.
Oh, people used it and they mentioned that didn't really help much. Surprising. Yeah, surprising. The first solution did not use weather data. The first and second didn't use it.
But how did they encode the data from weather? It's sunny or?
I think it's temperature. So the question is, so I'm just going to go. The question is, how did they actually use the weather data? Sorry, because we are short on time. Yes, and the answer is that the temperature. They use temperature. All right, so let's look at top ranking solutions. So all of them use boosting. Surprise, surprise. Nobody reported they got good results using deep learning. And weather data, like I said, wasn't very helpful. But the key, as I mentioned, was adjustment for the Golden Week. And the person who suggested that named it holiday trick, and people who used it, everybody who applied it, they reported that they got a boost from this holiday trick. So let's look at what holiday trick is. So here I've shown the Golden Week. These are Saturday, Sunday, and these 3 days are public holiday, meaning that they have holiday flag set to 1. And these 2 days are not, they are working days. They have holiday flag set to 0, okay? So the key idea is very simple. The idea is that we need to treat these days like Saturdays, right? Because Saturday is a day that is holiday, and the day after it is also holiday, so people tend to go crazy, right? Whereas if we don't, the model, whatever model we are using, will treat this as a day that the day after which is a working day, right? And this is gonna break the logic. So this is insight number 1. Insight number 2 is that we should treat this day as a Friday, right? Naturally, kind of makes sense. So the person who suggested this hack, or not a hack, is this trick, suggests that we use the geometric mean of April 29th. So here, this Saturday, and May 13th, this Sunday here, take this geometric mean. In case you are wondering what geometric mean is, that it's the multiply the product of two numbers square rooted, right? It's geometric mean. So we take the geometric mean and use that as the number of visitors for May 3rd, 4th, and 5th. And for May 2nd, this day, we use this Friday here and geometric mean of that number and this day, and use that for Tuesday. And so in case you're wondering why these days and not these 2 days, I don't know why. If you have an idea, tell me. Probably because they did an experiment. I'm pretty sure they overfit or they fit for the leaderboard. And this is coming based on experiment, because I didn't see any explanation for this. So, yeah.
I have a few questions. You say you're multiplying only 2 days. Is that what they did, or every? So,
for these, yes.
Oh, and then to the geometric mean of it.
The geometric mean of, yes. For example, this day and this Saturday, right?
Yeah.
This is the formula is here.
And then used it for all, like interpolating all those other results?
Not interpolating. So we have one single, so predictions happened, right? So we did the predictions. Now we want to adjust the predictions, right? Yeah. So this is happening post-prediction. Now we want to bump up our predictions because we have very likely underpredicted the number of visitors for these days, right? So what do? We actually replace our predictions with this geometric mean, right? Is it clear? Okay.
So just maybe like an insight as to why they didn't use maybe there's a bit of bleed over from Golden Week into the next weekend, and so that would still be a bit of an outlier for that weekend.
Yes, that makes
like a normal Saturday, right?
Exactly, that makes sense. Yes. So probably it's because there's some abnormality here coming from this crazy Golden Week. Maybe people actually stop. One explanation is that people are so tired, they actually stop going to restaurants on Saturday and Sunday. They just want to cool off. They just want to cool down. Yeah, they burned up. And so this is more indicative of the actual activity of Saturday, Sunday. Probably this is one good explanation for it.
I think here Saturday and Sunday are off by 1.
Oh, come on. But which one?
So does that mean that it's actually a Friday times a Friday?
No. Which one?
The 12th?
Yeah.
That should be the 6th is a Saturday.
Did you actually count?
Is a. I'm just trying to
Yeah.
think of the logic behind why
Sure.
you would times a Friday by a Saturday.
Yeah, so I know that, if these dates are off, ignore the dates. It's actually Saturday and Sunday. They actually use Saturday and Sunday. So if this is 13th, you're saying this is 13th and this is 14th. This is what you're saying?
Oh. Well, yeah, I was saying either that or it was Friday, Saturday.
Yeah, so anyways, the formula, then in that case, the formula should be 14th and 13th.
Oh,
yeah.
Okay.
Anyways, the geometry, the meaning is happening between Saturday and this Sunday. This Saturday and this Sunday here, and this Friday and this Saturday. This is,
Okay.
yeah.
Okay.
Yeah, Friday, Saturday, Sunday. Okay. All right, so we have a few minutes left. Let's look at the second place solution. If you look at it, it's a fairly easy, relatively small kernel. He averaged between 3 models. You can see the weights in front of it. The 2 regressors, gradient boosting regressor and k-neighbors regressor coming from scikit-learn times 0.3 plus XGB times 0.4. And he got second. He's used latitude and longitude, the sum of them, and he used date as an integer. So that's also an interesting thing. And then finally, the first place solution, he used light GBM, and he defined tons of exponential features. You can see, so here, these are the bases, and the exponents are of course features. So he defined exponential features over all of the features that we talked about. And he also defined an insane number of window statistics. So different sizes of window with different shifts throughout this time frame. My laptop has 20 gigabytes of RAM. I tried to run this kernel on my laptop. It ran out of RAM and crashed twice. So you can imagine, and it's a fairly small data set. So you can imagine the magnitude of this data set. It's a crazy amount of data sets. And I think this is the reason that they managed to win, because they have so many different windows of different sizes defined, different shifts, that they actually managed to capture the seasonality and trends for different restaurants. And so you can imagine each different window captured one seasonality for one specific restaurant. And that's probably the way they managed to win.
Yeah, I can't see the windows you're describing, because I only saw the exponential features
it's not
regression.
It's not in it's not here.
How did it take those windows to capture those kind of recurring trends? I mean, the windows you're describing, I didn't.
Yeah, so take a window of 2 weeks, right? For one restaurant, take a window of 2 weeks starting from January 2017, let's say. Calculate the number of visitors, find the mean, max, median of all of those visitors, and add that for a feature. Add that as a feature. That becomes one feature, or a set of features. Mean, max, for that window, for that particular feature, like the number of visitors to a restaurant. Then take the same thing for genre. That becomes one feature. Yes, more or less like this. Yeah, all right, I guess I'm done.
I have one more question. The hole in the data, there's a missing data. So what did the winners do to that data point that's missing?
Are you talking about this?
There's this a long line of missing data. So
I guess this one? The missing data you're talking about?
No. There's one no one knows. You couldn't explain why it happens. Reservations, I think.
Yeah,
So what did the winning,
yeah.
this one, there, thanks, yeah, you're there, reservations. So what did the winning teams do to this? Did they take it out or did they leave it? So what did they do with
They both used it. First and second solutions, they both used this data.
They didn't do any adjustment to
No.
it?
They just used it as is. Yeah.
Okay.
Miraculously, it worked. Yeah.
Okay, great. Thanks. That was great.
Thanks.